Okay, so as everyone, I'd like to first of all begin by saying happy birthday to Professor Dani. It's always been a pleasure to read his papers, and they've had a big influence on my work. But my talk today is sort of off topic from the rest of the talks we've heard last week, and probably the talks we'll hear this week. So please, hopefully it'll be elementary. So please stop me at any time if I stop making sense. My co-authors. So this, I guess over here, I'm going to put definitions so I don't erase them. This is about nearly uniform covers. My co-authors are Ordentlich from Jerusalem. He's a electrical engineering professor, and Oded Legev from New York, NYU. He's a computer scientist. And so, so what is the topic that I want to discuss? So this is about covering, we have a convex body, and we have a, so let's call it K. So K will always denote, oops. A convex bounded set in Rn. We have a discrete set, let's call it L. And a very classical problem, which you've probably all heard at least a little bit about, regards whether one can pack copies of K in space disjointly by translating by elements of L, and how densely can we do this? And there's a dual problem. Can we cover the space Rn by translates of K, where you translate by elements of L, in such a way that the overlaps are small? So let me give you some definitions here. So K, the pair KL is called a covering if the translates of K by elements of L cover all of Rn, the set KL is called a packing. If the translates of K by elements of L are pairwise disjoint. And we are going to be interested. So the classical problem, as you may have heard about, for example, famous work of Thomas Hales, where he's discussing the optimal packing of three-dimensional space, the works of Wierzowska, where she talks about the optimal packing of space in dimensions 8 and 24, for which she was recently awarded the Fields Medal. So this is kind of a very, very classical topic. It's in Hilbert's lists of famous ICM 1900 list of questions, and so on and so forth. The covering problem, how do you cover space so that you minimize the overlaps, is also very, very well studied, and it's sort of a dual problem to this problem, and I'm going to be focusing on coverings, okay? And I'm going to be interested today in covers which are almost uniform. So I'd like to give some definitions that explain what I mean by almost uniform. So there's a function, which I'll denote by nkl of x, and this measures the number of times the number of L's such that x is in K plus L. Okay, how many translates of K hit our point X? Okay, so X is a point in Rn, and this is a K and L are usually thought of as being fixed, and X is the variable of this function. And we want to define an average for this quantity. So this average is the lim as t goes to infinity, 1 over the volume of the ball of radius t around the origin, integral over the same ball, this function. integral with respect to Rn. The volume is Lebesgue measure on Rn. The integral is with respect to the volume on Rn. Of course, this limit might not exist. So when I write this down, I'm assuming that the integral exists. And then I'll say that the average covering number exists if this limit exists. Okay. Now, if you give me so what we're interested in, so on average, points get covered nkl number of times by this system of translates. Well, maybe before talking about the nearly uniform covers, let me talk about the special case of L being a lattice. So you all know what a lattice is, but let me still define it. A lattice is, it's the Z-span of a basis of Rn. So we take n linearly independent vectors in Rn, and we look at the span of these n vectors, where this means that we're only taking the span where the coefficients are integer coefficients. So this is the same as saying that we take the lattice of integer points, Zn, and we apply a linear transformation to it, A, where A is the matrix. These columns are the VI. And there's a particular convex body that you might consider in this kind of a situation. Let's let K be the image under A of the unit cube. And I took the unit cube closed on the left, open on the right for a reason. If you take this unit cube and you translate it around by elements of the integer lattice Zn, you're exactly covering space. Every point gets covered exactly once with no overlaps. So what that means in our notation is that this is both a covering and a packing in that situation. And this function is a constant function. It's everywhere equal to 1. Okay? And so the average is equal to 1. And so such a set, if K L is both a covering and a packing, we'll call it a fundamental domain. So in this particular case, I'm giving a definition, but I'm also giving an example. In this particular case, this would be one possible fundamental domain for the lattice L, which is A of Zn. And its volume is the covolume of L. So covolume of L is defined to be the absolute value of the determinant of A if L arises in this form, which is exactly the volume of this set. It's the volume of a fundamental domain. Of course, here I chose a particular fundamental domain, but it's a fact that all the fundamental domains have the same volume, and this is the covolume of the lattice. So that's another piece of notation. And let me also specify, so we're going to be interested in nearly uniform covers and nearly uniform lattice covers. But when we say lattice covers, we mean that the set L is a lattice. We only are interested in translating by points in a lattice. So more notation for the lattice case. Let's let, maybe I'll put this still on this board. The torus defined by L is the quotient of Rn by L. So topologically, this is a torus, but its geometry depends on the specific lattice that we choose. Pi is the projection. And so in this situation, KL is a covering if and only if K is projected onto the quotient and K is a packing if and only if the restriction of pi to this set K is injective. So in other words, when you're packing when this function n assumes only values 0 and 1, and you're recovering when this function n always assumes values at least 1, and that's equivalent to these two things. And so with these notations, I want to give a formula for that average covering number. So let's let proposition for L a lattice, this number lnk, which I define this average covering number. First of all, it exists, and it equals the volume of K divided by the co-volume of L. Okay. In particular, if L has co-volume 1, sorry, I think I noted the case. In particular, if L has co-volume 1, then this number is just the volume of K. Okay, so it's a good thing to remember that in interesting cases, the function nkl, which I wrote over there, is just the volume of K. Okay, so this is you can just this is a good exercise if you haven't seen this before. The idea here is that the limit that I wrote down on the right-hand side of the board exists by periodicity. You're covering a fundamental domain, and this is the you can make a computation that says that this is the number, the average number of points that a point in a fundamental domain gets covered, where the average is taken with respect to the Haar measure on this probability Haar measure on this quotient torus. And so that's a little computation that you get this formula. And by periodicity, if it exists on one fundamental domain, since the whole picture is periodic, the limit exists everywhere, and it's equal to this number. Okay. So now let me make a definition that encodes how uniform the cover is. So this is going to be denoted by eta of KL. I'm going to call this the smoothness of the cover. So this is the maximum over, or the sup, I guess, in general. That's sup over X in Rn of the, well, I guess it's maximum. Maximum of the value of this function at the point X divided by its average value, subtract 1. So on average, points get covered this number of times. Some of them get covered more times. Some of them get covered fewer times. We're taking the quotient. This is usually, this on average, this number is 1. We want to know how far it deviates from 1. So the smaller this is, the more uniform the cover is. Okay. Let's see if I want to put another definition here. So you'll notice that if this number is less than 1, then if this number here is less than 1, then this cannot be 0. So that means that the numerator here cannot be 0. So that implies that this is a covering. So I'll write that down. Let me write that down over here. Eta KL less than 1 implies that KL is a covering. And the smaller eta is, the finer or the smoother or the more uniform the cover is. So let me write down some natural questions about this smoothness or uniformity parameter. And those are the questions that I'd like to discuss in this lecture. So question 1, we fix these three numbers, k, l, and epsilon. So now it might be that the covering or the system of translates covers with uniformity epsilon, and it might be that it doesn't. If it doesn't, we might dilate k, make k larger, and it's going to get larger. And as it gets larger, it's going to cover space more and more smoothly. And we want to know how large do we have to make it. How large do we have to make k to make the cover smooth? So so I'm going to formulate it precisely. Let k prime be a dilation of k by some parameter r. And the question is, how large does the volume of this dilate have to be so that the smoothness is less than epsilon? So I'll show you some pictures just to make sure we're all on the same page. So can we lower the screen, please? Okay, so what you're seeing here, the black dots represent a lattice. The red k is my red. The red color is the boundary of k. So k is just a ball in this two-dimensional example. And in this example, we're not covering space and we're not packing. These points are left uncovered. We have overlaps here, so it's neither a covering or a packing. Some points are covered 0 times. Some points are covered once. Some points are covered twice. So the function nklx assumes 3 values, and you can compute what this eta might be. We can make this dilated set so I think this is a new picture. We make the dilated set bigger, and it starts covering more of the space. And when we make it even larger, now it's a covering. All points are being covered. So we're progressively making the balls larger. And if we make them much, much larger, say 10 times larger, so until the area of the circle, say, is 100, then on average, points will be covered 100 times. But you won't have points which are covered 50 times, or points will be covered either 100 times if they're in the interior, or on the boundary, maybe they'll be covered 98, 99, 101, 102 times. But the deviation from the average is going to get smaller the bigger the ball is. So as we make this parameter r larger, epsilon is going to go down. Okay? And that's what we want to capture. When do we start getting epsilon uniform covers? This is a good time for questions. Are the definitions clear? Okay, so we can raise the screen, please. And let me make a definition. The function psi KL of epsilon is this infimum. It's the smallest dilation, the volume, the smallest volume for which this dilation gives us an epsilon smooth covering. And the second question that I'd like to raise is, so now we're not fixing. Now we're not fixing L. We're just fixing K and epsilon, and we're searching for an L for which this cover is smooth. We're searching among lattices. So let's let's stick, in these first questions, let's stick to the case where the translates L form a lattice. So the question is, for which T does there exist lattice L so that psi k of epsilon is less than T. And one more thing to notice about these, this function psi k of epsilon, it's a geometric function. So in other words, it doesn't really depend on k, on the volume of k, because we're going over all dilates of k. So in other words, if you replace k by any dilate, it's going to give us the same function. If you replace L by any dilate of L, it's going to give us the same function. If you replace k by a translate of k, if you move k around, it won't matter because the cover will just get shifted, but the function won't, the values of the functions will be the same up to a shift. So this is sort of a natural function. Okay, this comes from the computer science literature. In the computer science literature, what people do is they, it's a kind of a cryptography protocol, and they send you a point in Rn, and your goal is to find points in the lattice which are close to this point in Rn. So you can think that you're broadcasting an element of a lattice shifted by an element of the set K. And if you have smoothness, there's no good answer to that question. You have lots and lots of, it sort of means that all x's behave in the same way, and there's no, this doesn't distinguish the x's. So anyway, it's a computer science terminology. I should say that both these problems of covering and packing are very intensively studied both by electrical engineers and computer scientists for completely different reasons. So, and the mathematicians, unfortunately, are not talking enough to the computer scientists, and they're not talking enough to the electric. So there's not enough communication going around. Okay, so the electrical engineers, so I'll tell a joke if you don't mind. So the electrical engineers study this. So you put down antennas, and if you have a good packing, sorry, if you have a good covering, that means that every cell phone gets coverage. And if you minimize this this covering volume, then you're saving energy. And the engineers, since they're practical people, they're interested in optimal antenna configurations as a dimension of the world goes to infinity. So that's the joke, but they are very actually interested in that. And of course, this is a bit of a joke. It's not just about antennas in three-dimensional space. It's about coding problems, coding and transmission problems. All right, so the third question. So what this is saying, i.e., we want to estimate. Here's another way of formulating this question. We'd like to estimate the infimum of this function psi k L of epsilon, where k and epsilon are fixed and L varies. And as I said, we don't really care about L up to dilation, so we can allow it to vary in the set, which I want to call curly xn. This is SLN R over SLN Z. Space of lattices for volume 1. Okay, so this is basically the question that I'm asking you. Is this board still visible on the? Okay, so let me formulate a third question, which seems harder a priori. So let mu n be the natural measure on this homogeneous space SLN R over SLN Z. So I'm going to call it. I mean, people have called it the Dhar measure. I think it should be called the Dhar-Siegel measure. I think for this audience, I don't need to define it. It's the unique invariant SLN R invariant measure on the space of lattices. And the question that we now want to ask is question 4. Fix k and epsilon. And so estimate the measure in the space of lattices of the lattices for which this function is less than t as a function of t. All right? Oh, good question. That was question 3. No, this is question 3. So what I'm asking is, how large does t have to be so that for most lattices L, a dilate of K volume, dilate, let's call it K prime, of K of volume T, gives an epsilon smooth covering. This is the question. And the fourth question, for which I have little room, but it's enough, question 4, same kinds of questions for L general. In other words, not necessarily a lattice. Okay, so these are the questions that I'd like to discuss. Let me formulate our results. The first theorem that I want to call Theorem A is about question 3. So the Theorem A is, I'm going to state 2 theorems, Theorem A and Theorem B. Theorem A is going to be about lattices. Theorem B is going to be about general M. Pardon? I think it says not necessarily a lattice, but yeah, not. So same questions for general L, not necessarily a lattice. Oh, before that. So that for most L, a dilate K prime of K, of volume T, satisfies that the smoothing parameter eta K prime L is less than epsilon. Okay? All right, so Theorem A, we take 2 parameters, epsilon and sigma. So, you know, this is going to seem a little bit technical, the theorem, and I'll try to sort of explain what this is talking about gradually, so don't be intimidated. So we fix 2 parameters, epsilon and sigma. We take a supremum over all convex sets in Rn, K, and for each of them we use the Haar-Siegel measure to measure those lattices giving us the psi function less than n to the power 3 plus sigma. And we prove that this supremum goes to 1 as n goes to infinity. So how should you think about this? You should think about the last line there that people couldn't read very well. Take t to be this number. It depends on the dimension. It's n to the power 3 and a little bit more. So when the volume of convex bodies is a little bit more than n cubed, where n is the dimension, then you can find lattices for which the covering is epsilon smooth. And I should have said, yeah. And you can find that with bigger and bigger probability over this Haar-Siegel measure as the dimension grows to infinity. Okay? So that's the sorry? The dimension of Rn is n, always, in this talk. N will always be the dimension. This is a limit as n tends to infinity of this expression. There was a further question here, but let me formulate some corollaries, and maybe after I formulate, this is the general theorem. Maybe after I formulate the corollaries, it'll be easier to digest. If not, please ask. Sorry? Yeah. So I'm going over all convex bodies K. So if I'm saying that some supremum is going to 1, this means that this expression holds no matter what K is. It's completely uniform in K. So fix your favorite convex body, whatever it is. Now ask yourself, if I randomly generate lattices using the Haar-Siegel probability measure, what's going to be this parameter? In other words, am I going to satisfy the property that there's a dilate of that volume, which gives us a smooth covering? And this is saying that if the volume that we care about is n to the power 3 plus sigma, again, this depends on n, but if the volume is in this range, then with high probability, we do get epsilon smooth covers for any epsilon. Sigma is not 0. Oh, what happens? Good question. I'm going to get to, there's some open, we didn't solve the whole thing, of course. Yeah. We don't know if this is optimal. So basically, it would be interesting to see if this can be reduced. And this 3 could be brought down. And we're going to see that that's related to some very interesting other questions. Okay, so this is the theorem. Let me give you some corollaries. And after I give you the corollaries, maybe it'll be easier to digest. So first corollary. So the way I'm going to give you these corollaries is I'm just going to specialize this statement to various special cases. So the first specialization is basically the idea is that sets of positive measure are not empty, right? So if I have a statement saying that this measure goes to 1, in particular, this set in here is not an empty set. So what you get from that is, again, if you fix epsilon and sigma, and you take n large enough, where large enough just means you take n large enough so that this number becomes positive. As soon as this number becomes positive, the set in here is not empty. So then for any convex K, there exists a lattice L. Sorry, any convex K in volume n to the 3 plus sigma, there exists a lattice of covolume 1 such that eta AL. Okay. Clear? For any convex set K in Rn, I should have said, of course, of this volume, you can find the lattice. The lattice depends on the convex set, of course. This is the uniformity in this soup here. For any convex set K, there exists a lattice. The lattice is going to depend on K. Okay. So let's specialize even further. corollary 2. I want to specialize to epsilon less than 1. The number, any epsilon less than 1. The number 1 is important because, as I said, as soon as this eta parameter becomes less than 1, we know that we have a covering. So let's just talk about coverings and not talk about their smoothness. For any sigma, for any or let me write it this way. Supremum over K of the probability that when you choose a lattice at random, you get a covering. Sup K, volume of K equals 3 to the n sigma. The probability that you get a covering goes to 1. So if you're taking any convex set, and sorry, this 3 to the n plus sigma looks like n to the 3 plus sigma, but it's not the same. So what I really meant, you'll see why this is an important distinction. What I really meant is n to the power 3 plus sigma, not 3 to the power. Okay, so again, if you take convex sets and they have this volume in Rn, their volume is a little bit more than n cubed, then they're going to cover with very large probability going to 1 as the dimension goes to infinity. And so a kind of corollary 3, both specialization. So in other words, I take epsilon less than 1, and I just remember that non-empty sets, sets of positive measure are non-empty. Then what I'm going to get is for any sigma for all n large enough, for any k, of volume n to the 3 plus sigma, there exists L for volume 1 such that KL is a covering. So you should think of the theorem as being a kind of a very smooth extension of this result. When the convex body has this volume, n cubed and a little bit more, then you can find a lattice for which you can get a covering. Okay, so let me just say a few words about the history. Some of you attended my lecture series in Mumbai a few months ago, so this might not be interesting for you, but maybe the other people in the audience don't know. So let me say a few words about this last corollary, just to put everything that I'm saying in some kind of historical context. So it's a very famous problem and this is also related to the previous question about the optimality of this 3. So it's a very famous problem to estimate the growth of the volume for which you have cover. So I'm giving you a dimension n, which you should think of as being large. I'm giving you a convex body of some volume where the volume is a parameter. Does there exist a lattice so that of covolume 1 so that these translates cover? That's a well-studied question by many people, and particularly there was some work in the 50s by Rogers, and it was went unimproved for many years. This is results from 58. So I'll just say it in this form, same as corollary 3, but with n to the 3 plus sigma replaced by n to the constant times log n. So this was a kind of a well-known result of Rogers from the 50s. And you see that n to the log n is much bigger than n to the 3 plus sigma. This result was not improved for a very long time. And then in fairly recent work, and let's just write in prior work, and this is also with the same co-authors, we improved Rogers bound to a constant times n squared. So the world record at the moment regarding the statement here in Corollary 3 is not in the new paper that I'm talking about right now. It's not in Corollary 3. It's in this statement. The world record currently is a constant times n squared. It's a very interesting problem. There are non-matching lower bounds. The lower bound is n. So what's going on between n and n squared in that regime is wide open and very, very interesting. And it's related to the question that you asked. So 3 is not optimal. We don't know if 2 is optimal, but that's the world record at the moment. So this is sort of background that you should keep in mind. And the new work that we're now discussing is not really about Corollary 3. I just put it up here so that you could compare. It's really about when do the covers become smooth, epsilon smooth for any epsilon. So again, if we fix some small epsilon, the covers become epsilon smooth when the volume is a little bit more than n cubed. That's what we know at the moment. We start getting covers when the volume is around n squared. And it's very interesting to figure out what's happening in between. Okay? Yeah, theorem A doesn't beat, pardon? Correct. For going from general covers to epsilon smooth covers, we lose a 1 in the power here. Well, a little bit more. Exactly. Pardon? Yeah, for the sphere, Rogers has a better bound. The bound is n squared times log n to some power. So no, wait, sorry. N times log n to some power. So the result for spheres is better than the general result by a factor of essentially 1. There's a lower bound for spheres and for general shapes. The best lower bound is on the order of n. So for spheres, basically, Rogers almost closed the gap completely. And this is again in 58. But for general convex bodies, this was open. So whenever I write C, I should have said that earlier. Thanks for the comment. Whenever I say C, it's not always the same C. Okay, so this C is not necessarily the same as this C, and it's not necessarily this C. I just mean some constant independent of dimension. And so yes, here, this, I don't know if you meant this C, but this C is definitely greater than 1. And we have sort of explicit formulas for these Cs. And in fact, Rogers and Schmidt and a bunch of people were very, very caught up in this back in the 50s, and they were publishing papers just about improving the Cs. Quite a number of papers. So this was very, very, very well studied. And then it was sort of left aside because there were no improvements. And maybe, depending on time, I'll be able to tell you a little bit about why we were getting improvements all of a sudden over these old papers of Rogers. Questions about this statement of theorem A and its corollaries? Okay, so actually, I don't know. Is that clock correct? So I have 10 minutes? Okay, I'm see that I'm not going as fast as I would have liked to, but okay, that's life. So let me formulate theorem B. Theorem B is about general L. So not, in other words, not necessarily lattices. So so you're going to see that for general L, we can do much better than n to the power 3. So for any convex body, volume C times n times log n, so quite close to n, we can cover smoothly. So there is an L. Oh, maybe I should, oh, this is, sorry. For any convex K, what I said is sort of correct, but not consistent with my definition. For any convex set K, there is L in Rn, for which this NKL quantity limit exists. It's equal to C times n log n, and this eta function is less than epsilon. So in other words, you should think of this, as I said earlier, you should think of this number NKL as secretly measuring the volume of K if L is assumed to be of density 1, whatever density 1 means, which I didn't define. So that's what happens in the case of lattices, and that's what you should think of as in general. So this is like, once the volume of K is n log n times a constant, then and L is, you can find an L of covolume 1, whatever that means for general sets, so that you can cover space smoothly up to an error of epsilon. Okay, that's theorem B. So you're seeing here n log n, and there you saw 3 plus sigma, so it's much better for general sets. Now, comment, in all of this business, people expect general sets to give better covers, better packings, et cetera, in large dimensions than lattices, but there are very few proofs showing that. But this is consistent. So in most of this work, there are different bounds for lattices and different bounds for general sets, and the bounds for general sets typically are much, much better. And this bound, I don't want to write down the history of this problem, but this bound, you can specialize, and you just prove that there are covers using this method, not necessarily epsilon smooth. And our bound matches the old bound of Rogers for that problem. And up to the value of the constant, perhaps, we match the value of Rogers. And our proof is actually, this proof of theorem B is much simpler than the proof of theorem A. And in fact, it's quite close to what Rogers did. Okay, that's a good question. L is some discrete set. That's what I mean by general L. But you're going to see that when we do the analysis, L will be not at all general. It'll be a periodic set. So I don't know. I'm sort of low on time, and I'm thinking of what I should say. So yeah, so I want to give you some ideas of the proof. So let me start with answering that question. So when we talk about general L, a priori, we just mean some discrete set. But you know, there's lots and lots and lots of discrete sets in Rn. And how do you analyze them? They're sort of unstructured. The way you analyze them is you restrict to so-called periodic sets. So L is L0. Let's call it L1. L1 periodic if L1 is a lattice. And L is the disjoint union of some number of translates of L. So In fact, in this entire literature, as far as I can tell, when people do packings and coverings working with general L and they want to prove anything, this is the collection of general L which gets used. This is much, much easier to analyze than general discrete sets for which we have very little structure. So how do we prove? Yeah, let me think about what I want to say about the proofs. So, okay, so I apologize. This is going to be a little bit of hand waving. How are we proving these results? So there's a common approach to Theorem A and Theorem B. What you do in both cases is you transform the question into a discrete question. So I'll just draw a picture. You find, so discrete question for L1, sorry, L prime. A fine lattice. And what I mean by fine, I mean a lattice of very small co-volume. So lots and lots and lots. You should think of a dense, very dense lattice in Rn. You try to cover points of L prime by the system so instead of covering all of Rn, we make some analysis which says that we can reduce it to another problem of not covering all of space, but just covering a fine mesh, okay, of points which are points on a lattice, and they're not too far away from each other. And that's sort of the first step. I was going to do it more formally, but I'm running out of time. Once you've done that, which point over there? So the way we're going, so I'm going to be discussing the proof of Theorem B. So now, very briefly, so now we're being given set K in some large dimension, and we're trying to find a set L for which we get a smooth cover, and we'd like to not dilate, to have to dilate K too much. So what we do is we first choose L1 so that we first find a lattice L1 of covolume 1 so that, so assume that the volume of K is 1. Sorry. So we first find a lattice so that essentially if you inflate K by a little bit, you cover all of space. And if you shrink it by a little bit, you get a dense collection. So can you do this with some shrinking and dilating parameter R, which is independent of n? Yes, you can. And this is sort of a classical bit of analysis from the 70s. So I'll just write down Butler 72. I mean, this is there's work of Butler, who was a student of Rogers, making this possible. And now what kind of, I'm going to cover L prime. I haven't defined L prime yet. Now I'm going to find L prime. This is covering Rn. And now what I'm going to do is, okay, you'll see. So now what I'm going to do is I'm going to define L prime to be 1 over n L1. So I said L prime is going to be a fine mesh. So this is this very, very fine mesh. So L1 is a sublattice of L prime, and L prime over L1 contains n to the n points. And the picture you should have in mind, if you're taking L1 to be the integer lattice, is sort of an n by n, a cube of size 1, where you put n to the n equally spaced points. So now what you're doing is you're projecting k shrunk by a lot into this, shrunk not by a lot, sorry, shrunk by, where did this go? Shrunk by this amount. So k projects onto this cube. And your goal now is to choose the cosets Li, which I wrote down on the right-hand board. L is, remember, L is the union the set. Your goal now is to choose the cosets Li so that k is covering essentially uniformly this discrete set of points. So the picture to keep in mind here is that k projects here, and some points get covered. So the points that get covered, I'm going to draw in red. And now we're going to think of translating this red set around with elements of k so that this entire discrete grid gets covered epsilon uniformly. That's what the problem becomes. And we can do, and the way to solve that, since I'm running out of time, I won't go into it. The way to solve that is to just define, it's a probabilistic argument. You show that with high probability over these possible translations, points get covered, if you randomly choose the translations, the expected number of times. And there's some independence going on and a Chernoff bound, and it's quite easy probabilistic analysis to do this. And I'm 1 minute over time, so but I need to tell you the keywords. So the way to deal with theorem A, in theorem A, we can't just choose the cosets Li at random. We have to form a lattice. L should become a group. So the way to do that, the restriction here is that the Li's are a subgroup of this quotient group, L prime over L. So in general, subgroups are difficult to handle. But if n is a prime, this quotient, L prime over L1, is essentially the discrete vector space Fp to the n. N is P, and it's a prime. So this is, so if n is prime, L prime over L1 is basically the same as an additive group. It's exactly the same as Fp to the n. It's addition mod P. And choosing the cosets so that you get groups is exactly as the same as choosing vector subspaces. So what we're trying to do is push this red set K around with vector subspaces so that it fills up space essentially uniformly. And that's a studied problem in combinatorics. This goes under the discrete Cauchy problem. And there's been, so I'll just write down two very important names for theorem A. We use Dhar and Dvir, new result from 2022. Dvir is like the world's leading expert on the so-called discrete Cauchy problem. The discrete Cauchy problem is the following problem. You're given a set K in a discrete vector space like this one, and your goal is now to push it around using, it's not usually stated in this form, but it's equivalent to what I'm stating. Your goal is to push it around by elements of a vector space so that it covers, and you want to do that with vector space, which is as small as possible. So Dvir is the expert. Dhar is his former student, who's also an expert, and this is a very deep recent paper, which they proved in response to our questions. And with this new input, we can prove our result. It's a key input, and it's far from trivial. And last sentence I'd like to say is, I mentioned earlier that why couldn't Rogers have proved what I called Corollary 3 back in the 50s. The reason is that Dvir was not active in the 50s. I don't know if he was born in the 50s, so probably not. So what we're using in this recent work are breakthroughs on this discrete Kakea problem. That's what feeds into all of our work. And this tool was not available to Rogers back in the 1950s, and that's the new ingredient. Okay, I'll stop here. Thank you for your attention.